Welcome to Introduction to Ecology, Lesson 10. At the end of last class, we talked about populations being dynamic, about populations changing in time. And so the focus of today's lecture, and indeed the next couple of lectures, will be on population dynamics, on studying population change through time. To do that, we're going to introduce what's known as a life table. And a life table is basically a table that provides a summary of how survival and reproductive rates vary with the age of an organism. So typically when I'm making a life table, I'll start with one column for the age, and then I'll have another column that tells me the number alive at each age, and then a third column where I calculate what's known as the survival rate, a fourth column where I calculate what's known as survivorship, and you need to keep survival rate and survivorship separate and straight in your mind. I guarantee you some of you will get those confused on a test, and they are different, and you need to know the difference. And finally, the final column is typically fecundity. So great, we have a table. Where do we get the numbers from? How do we make a life table for a particular population or for a particular species? Well, there's basically two different ways. The first way that we can make a life table leads to what's known as a cohort life table. And to make a cohort life table, we start with a group of individuals that are all the same age, and we monitor them for many years. So let's suppose we start with this plant population, and we start with our seedlings. Typically you start at age 0. And we might have something like 10 seedlings in 2018. So this is the number of individuals that are going to be in our cohort. That's the total number of individuals we're tracking. We might go back then next year in 2019, and we look at the number of those seedlings that have actually survived and grown into plants. And so if I count those up, I end up with about 8. All right. So that's the number of individuals that survived from the first year, or from age 0 to the first year. They survived through the first year. I then go back in 2020 and I count and I see now I've got 6 plants left from that initial cohort. And so that's the number of individuals surviving to the beginning of the second year. Go back in 2021 and maybe I only have 5 plants left from my initial cohort. That's the number of individuals surviving to the third year. In 2022, I'm down to 4. Maybe I go back in 2023 and I find all 4 of those are still alive. But then when I return in 2024, I'm down to 2, and then none of my cohort is alive by the time I reach 2025. So now I have tracked that single cohort that started out all the same age, and I've looked at the number that survived from one year to the next. With that information, I can now calculate what we call survival rate. Survival rate is the chance or the probability that an individual of age X will survive to be age X plus 1. It's the probability of making it 1 year older from the age you're in. So if I took a look at the survival rate S0, that's the chance that an individual of age 0 will survive to be age 1. So I had 10 age 0 individuals. How many of them made it to age 1? Well, 8 of them did. And so my survival rate will be 8 over 10, or 0.8. So that's my S0 survival rate. If I look at the next survival rate, the S1 survival rate, that's the chance that an individual of age 1 will survive to be age 2. Well, I had 8 age 1 individuals. How many of them made it to their second year? 6. And so my survival rate for my age 1 individuals was 6 over 8, or 0.75. Do this one more time. If I'm interested in my S2 survival rate, that's the probability that an individual age 2 will survive to be age 3. So again, I had 6 individuals that were age 2 and only 5 of them made it to age 3. And so my survival rate for age 2 plants was 5 over 6, or 0.83. So you can go on and on like this, filling out the survival rate for each different age based on the number that made it to each different age. And if you do that, you get these numbers. I'll let you try that at home. And of course, once you have a survival rate of 0, you can't go further. And so that last line in the table should be blank. So that's survival rate. And again, some of you on the exam will get survival rate and survivorship mixed up. I guarantee it. I will put money on it. Survivorship is a little bit different. Survivorship is the proportion of individuals that survive from birth to age X. So not from one year to the next. Survivorship is all about lasting from birth to a particular year. So if I now take a look at my year 0 survivorship, that would be the proportion of individuals that survive from birth to age 0. Well, that doesn't take much. Basically, all of the organisms that are born, all of the plants that were born, survived to age 0. So the survivorship for your age 0 individual should always be 1. If it's not 1, you've messed up. Little bit more tricky when we move to age anything bigger than 0, age 1, age 2, age 3, age 4. So the survivorship for age 1 is the proportion of individuals that survive from birth. So we had 10 born to age 1. So that's 8 survived to age 1. My survivorship is then 8 over 10, or 0.8. Let's do the year 2 survivorship. The year 2 survivorship is the proportion of individuals that survive from birth, so there were 10 at birth, to age 2. There are 6 age 2, and so it's 6 over 10, or 0.6. The year 3 survivorship is the proportion of individuals that survive from birth to age 3. So again, 10 were born, 5 make it to age 3, and so my survivorship is 50%, or 0.5. And again, you can go on and fill this chart out based on the number of alive at each different age. And I will again let you try that at home, but you should get these numbers. All right, so that's survivorship. The last column will be fecundity, and this is the average number of offspring produced by a female while she is age X. So here are my little seedlings. Typically with plants, not a lot of year 0 plants are going to make babies, so that's often 0. However, when I come back the next year, we can take a look. Do any of these plants, any of the 8 plants left, make any babies? If they don't, fecundity is again 0. I go back in 2020 and I look for babies. How many babies do we make? If I count that up, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I see 12 babies, and I had a total of 6 plants. So on average, each plant is making 2 babies. Now notice that some plants make 4 babies and some make none, but on average, each plant is making 2 babies. I go back in 2021 when my cohort is age 3, and I count the number of babies they're making. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I have 15 babies and a total of 5 plants. And so on average, each plant is making 3 babies when they're age 3. I can go back in year 4, count the babies, divide by the number of plants. Again, in this case, each plant on average made 3 babies. Go back in year 5, count the number of plants. In this case, we dropped a bit, 2. I go back in 2024 when my cohort is 6 years old. Maybe each plant only makes 1 baby. And then when I have no plants left in 2025, obviously I also have no babies. That line should be, again, a blank because I have no plants to make babies. So now I have completely filled out the life table based on a cohort, based on following individuals that started at the same age and then following them through time until no individuals are left. Now note, though, if I know the number alive at each age, I still can't fill out that final column, that final fecundity column, without knowing about their reproduction. So just knowing the number alive, I should be able to calculate survival rate and survivorship, but I will not be able to calculate fecundity without being told something additional, without being told how many offspring different organisms have. So that's a cohort life table. The other type of life table you can make is known as a static life table. And with a static life table, it's a little bit simpler. You don't have to monitor these organisms or this cohort for many, many years. You just look at one single time point, 1 year. You go in and you look at individuals of different ages. And so maybe I have a fish population in 2018. And again, I'm not going to go in for 5-10 years. I'm just going to look at them in 2018. And I'm going to say, well, how many year 0 fish do I have? And those are the smallest fish in this figure, and you can count them up. There should be 10. And then I say, well, how many year 2 fish do I have? And again, those are the second biggest fish, or the second smallest fish. If you count them up, 1, 2, 3, 4, 5, 6, I have 6. And that's the number of 1-year-old fish. I then look at the next age class, and in this particular drawing, those are your second biggest fish. So if I count those up, there are 4 of them. And those are the number of 2-year-old fish. And then I count my year 3 fish, and those are the biggest in this particular figure, and there's 2 of them. And then notice there's nothing bigger, so there's no year 4 fish. So again, I've looked only in 1 year. I've looked in 2018, but I've looked at the number of each different age in a single year. So again, I can go ahead and I can calculate survival rate and survivorship. Survival rate has the exact same definition in a static life table as it does in a cohort life table. It's the chance that an individual of age X will survive to be age X plus 1. So if I look at my year 0 survival rate, that's the chance that an individual of age 0 will survive to be age 1. And I had 10 age 0 fish, and I had 6 age 1 fish. So it's looking like about 60% of my newborns make it through their first year. If I then look at my year 1 survival rate, that's the chance that an individual of age 1 will survive to be age 2. So I had 6 year 1 fish, but only 4 year 2 fish. So in that case, my survival rate would be 4/6, or about 67%. And again, you can go on and fill out the table, just like you did before. I'll let you try that. You should get these numbers. And then, of course, just like in the cohort life table, in the static life table, the final row in the survival rate column should not be filled out. There's no probability of surviving past 4 years old. It doesn't make sense. There's no probability of surviving past 3 years old, and there's no 4-year-old fish. All right. Survivorship, again, we can calculate based on the numbers alive in our first column. But again, you got to be careful and not confuse survival rate and survivorship. So survivorship is the proportion of individuals that survive from birth, or age 0, to age X. So my year 0 survivorship is the number of individuals that survive from birth to age 0. That takes nothing, all of them do. So again, that number should always be 1. Your year 1 survivorship is the proportion of individuals that survive from birth to age 1. So I had 10 fish that were newborns, and I have 6 year 1 fish. So it's looking like 60% survive to year 1. My year 2 survivorship is the proportion of individuals that survive from birth, so there were 10 born, to age 2. There are 4 age 2 fish, so it's looking like about 40%. And again, you can go on and fill that out. I'll let you try that. You should get those numbers. Moving on to fecundity. Again, with fecundity, you need to be told things. So we're going to look at the number of babies born to each age fish. So if I take a look at my age 0 fish, maybe, and typically, they might have no babies at all. So often that row is 0. Sometimes very newborn organisms can actually give birth, but that's rare. If I take a look at my year 1 fish, I have to be told how many babies they have. So in this case, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 babies out of 6 year 1 fish. So on average, each year 1 fish was having about 2 babies. I look at my year 2 fish, and I have to again be told how many babies they made. So maybe they made 4. And so on average, each year 2 fish was having 1 baby. I look at my year 3 fish, and maybe between the 2 of them, they just had 1 baby. So in that case, I have 1 baby out of 2 fish. I have on average a half a baby made by my year 3 fish. It is okay to have fractions. And then again, I have no year 4 fish, so that line should be blank. It doesn't make sense to talk about how many babies are born from fish that don't exist. But again, knowing the number alive, just knowing the population structure, you can calculate survival rate and survivorship. You cannot calculate fecundity. I will have to tell you about the number of babies born to each of these different age classes, or I'll have to give you that information in some way that you can figure it out. All right. So both with the plant example and with the fish example, we talked about ages. Age 1, age 2, age 3 years old. It could be age 1 month old, 2 months old. It could be age 1 week old, 2 weeks old. It depends on the organism. But sometimes time isn't the best measure. And so when birth and death rates correlate poorly with time in chronological age, you can actually make life tables based on sizes or based on life cycle stages. So here I'm looking at an insect, and I have different life cycle stages. We talked about this a little bit when we talked about life histories and how we have sort of different sort of stages that a lot of insects go through. So here we have eggs, larvae, pupa, and adults. And I can count them up. I have 7 eggs, I have 4 larvae, I have 3 pupa, and I have 2 adults. And if this is all in one population that I measure in 1 year, then again, I'm making a static life table. It's a static life table based on stage, not based on age, but it's still a static life table. And I can go ahead and fill out my survival rate and my survivorship just based on the number of eggs, pupa, larvae, and adults that I have. I'll let you figure that out. Make sure you get the same numbers as I do. And then once again, I have to know a little bit about fecundity. Now, if you know anything about insects, you know that eggs can't lay eggs. You know that larvae can't lay eggs, and you know that pupa can't lay eggs. So all of those fecundities are 0. And then if I have 2 adults and 7 eggs, then on average, I'm going to have about 3.5 babies or eggs laid per adult. But again, you would have to know something about their life history to know that, to fill that in. From now on, I would expect you to realize that eggs, larvae, and pupa do not lay eggs. Only the adults lay eggs in these what we call holometabolous insects. All right. Now, static life tables are great, but they make very important assumptions. And unless those assumptions are true, you cannot calculate survival rate and survivorship based on the number in each stage or the number in each age. So, in order to calculate survival rate and survivorship from a static life table, from sort of information, measurements from a population in a single year, the population has to be at what we call a stable age distribution. That means you have to have the same number of each age year after year, and the population size has to be stationary. In other words, it shouldn't be growing or shrinking. If this is not true, you cannot construct a static life table. Okay? You cannot calculate survival rates and survivorships based on the number that are alive at each stage or at each age unless these assumptions hold. So that's very important. All right, great. We made life tables. We've calculated survival rates. We've calculated survivorships. Who cares? Well, the first thing that you can do with a life table is you can make what's known as a survivorship curve. And this is a graph of the number of fraction survivors as a function of age. So if I plot survivorship as a function of age, at age 0, everybody should have survived. Doesn't take anything to survive, no time at all. So we start with 1. And then we can look at age 1. How many survived? And in this particular example, 80% or 0.8. And then we look at age 2, 60%, age 3, 50%, age 4, 40, age 5, 40, age 6, 20, and age 7, nobody's alive anymore. So that graph there is what we call a survivorship curve. What's nice about a survivorship curve, you can plot it in terms of probability or fractions, but you could also look at a population of any size, say a population with 1,000, and you could say, how many individuals would I expect to reach age 1 or to be at age 1? How many individuals would I expect to reach age 2 or to be at age 2? And so in a population of 1,000, again, I might expect 600 individuals to be age 2 or 600 individuals to make it to age 2. And so again, that's the nice thing about a survivorship curve. With a population of any size, if I know the survivorship curve, I can predict sort of the number in each age are the number that make it to that age. And I can draw a nice line through it. Frequently, data is a little bit noisy, but you can draw a nice line through it and sort of get a sense for the trend. So all survivorship curves decrease, but they decrease differently. And that leads to 3 different classes of curves, what we call type 1 survivorship curves, type 2 survivorship curves, and type 3 survivorship curves. And we briefly touched on this a little bit in one of the previous lectures, but now you know how to make them. So a type 1 survivorship curve, this is typical in humans, and in this case, your young individuals, your newborns, your juveniles, your young adults, have a really high survival rate. So when I have a baby, I have a pretty high expectation they're going to live for a long time. And your death rates don't increase until you get to an old age. When you're a human, once you hit 75, 80, you might be pushing it. You might expect you're more likely to die than a baby or a 2-year-old. So that's a type 1 survivorship curve. With a type 2 survivorship curve, individuals have an approximately constant chance of surviving independent of age. So a 2-year-old might have a 50% chance of surviving, a 5-year-old has a 50% chance of surviving, and a 20-year-old has a 50% chance of surviving. So this is typical in birds, not all birds, but it's typical in birds. And that leads to that sort of straight line survivorship curve. The final type of survivorship curve is what we call type 3 survivorship. And this is where young individuals, juveniles, babies, die at a really high rate, but once they reach adulthood, they survive really, really well. So they have a very low probability of dying when they're really old. This is typical in trees. So the vast majority of little seedling trees don't make it. They die. But once you get to be a really big old oak tree or a really big old pine tree, you're very unlikely to die. If I think about the big oak tree at the center of Clemson campus over by the pool hall and over by BRC, I don't expect that oak tree to die next year because it's got a type 3 survivorship curve. All right, so across all types of organisms, type 3 survivorship is actually the most common. However, the sort of class of survivorship curve you fall into varies. It varies among species, like we see humans are more likely type 1, birds are more likely type 2, trees are more likely type 3. It even varies among populations though. So you could have one crow population that exhibits a type 1 survivorship and a crow population in a different area that exhibits a type 2 survivorship curve. So it can vary even within a species, even within a population. It can vary between males and females. And it can vary among cohorts. So, the blue jay population from 1970 to 1990 might exhibit one type of survivorship curve, but it may exhibit a different type of survivorship curve from 1990 to 2010. And so you can't necessarily make broad assumptions. You can't say all birds exhibit type 2, although they're more likely to exhibit type 2. And another important thing I want to mention is that these are idealized curves, and real curves frequently lie in between. So it won't be exactly type 2, it won't be exactly a straight line, but it'll be closer to type 2 than it is to sort of type 1. And so this is a spectrum. You don't necessarily fall into these discrete categories. All right. So all of this talk about life tables and varying survival and reproduction as a function of age leads to the idea of age classes and age structure. So an age class is the members of a population whose ages fall within a specified range. An age structure is the proportion of the population in each of these different age classes. So here I have my population of fish that we looked at before, and I can talk about the age classes, and I can talk about the age structure in this population. So my age classes, I could look at 0 to 1-year-old fish, I could look at 1 to 2-year-old fish, 2 to 3-year-old fish, and 3 to 4-year-old fish. Those would be 4 different age classes. And then the age structure will be the proportion of the population in each age class. And so I can plot that, and you see that I have a lot more age 0 to 1 fish than I do age 3 to 4 fish. So that's my age structure, is basically that graph. Often when we're talking about age classes and age structure, we we actually sort of divide the population a little more finely, we frequently look at sexes separately. And that makes a lot of sense because females and males sometimes exhibit different survivorship. And so, even in humans, at least historically, females have lived longer. And so it makes sense to separate females out from males in order to understand what's going on with that population. And so, again, I drew some bows on my female fish, and I can actually talk about the age structure for the females and the age structure for the males. And you can see that in this particular example, they're different. Some organisms they're not, in some organisms they are. In some populations they're not, in some populations they are. All right, great. We can talk about age structure. We can draw graphs that show how many more young organisms we have, how many more young fish we have than old fish, but what does that matter? Well, age structure is really important from the perspective of population dynamics because age structure determines how rapidly a population grows or declines. And I'll show you that by considering two examples. So let's suppose I have 7 fish in my population. In the first example, we're going to look at a population where I have 3 age 0 fish and 4 age 3 fish. So if I want to figure out how fast this population is going to grow, how many new babies this population is going to add in the next year, what I want to do is I want to look at, well, how many babies are each of my year 0 fish going to have? Turns out that's 0. So I have 3 year 0 fish, each having no babies. That gives me no babies. And then I have 3 age 3 fish, each having half a baby. Sorry, I have 4 age 3 fish, each having half a baby. And so 4 fish having half a baby each leads to 2 babies. And so over this entire population of 7 fish, I would expect on average to have 2 babies. That's not great. That's not a high population growth rate. Now let's take a look at the same species, the same number of fish in the population, 7 fish, but let's suppose all of the fish are age 1. So in this case, I have 7 age 1 fish, each having 2 babies. That gives me 14 babies. So all of a sudden, in the same species, with the same number in my population, I've gone from having 2 babies to having 14 babies. That's a very, very different population growth rate. That's a different number of newborns contributed in the next year. And so basically, the age structure of a population can be really important in determining how fast the population grows, whether the population grows or whether it's actually shrinking. So the next thing we're going to do is we're actually going to look at how we can predict population age structure from one year to the next and how we can predict population growth from one year to the next. Now to do this, I'm going to add one new column to my life table. So my life table before, I had the age, I had the number alive in each age, I had survival rate, survivorship, and fecundity. Now I'm going to add a second column that says the number surviving until the next year, or the number around in the next year for each of these different age classes. And with my life table all filled out, I have to fill out my life table first, but with my life table all filled out, I can actually predict the number of age 0 fish, the number of age 1 fish, the number of age 2 fish, 3 fish, 4 fish next year based on the number this year and all of this information about survival and fecundity. How am I going to do that? Well, first of all, I'm going to give these little symbols. So I'm going to call the numbers alive little n, survival rate big S, which is what I've always been doing. And to calculate the number surviving till the next year, I'm going to sort of take a look at the number in the age beforehand and the number that survives. So if I want to know the number of year 1 fish next year, I have to look at the number of year 0 fish this year and multiply that times the probability that those year 0 fish survive. So here I've got no year 0 fish. The probability that they survive is 0.6. Doesn't really matter because there's none of them. And so I have no year 1 fish next year. I don't expect any year 1 fish next year because I had no year 0 fish this year. All right, let's go to the next line. The number of year 2 fish next year is equal to the number of year 1 fish this year times the probability that those year 1 fish survive. So I have 7 year 1 fish this year. The probability that they survive is about 0.67. And so I would expect 4.69 year 2 fish next year. The number of year 3 fish next year will be the number of year 2 fish this year times the probability that they survive. So I have no year 2 fish, about half of them should have survived, doesn't matter, there were none of them, so I don't expect any year 3 fish next year because I have no year 2 fish this year. To move on, the number of year 4 fish next year should be the number of year 3 fish this year times the probability they survive. Well, I had none, and they also have 0 probability survival, so I don't expect any year 4 fish. And I filled it out. But you'll notice one row is missing. What do I do about year 0 fish? So year 0 fish don't appear by aging in from a previous age class, right? How do year 0 fish appear? Year 0 fish appear by being born. So in order to fill out that row, I need to look at fecundity. I need to look at how many babies are going to be born, because that's where I'm getting my year 0 fish from. And so in that final column, I have my fecundities. I'll label all those with F's. And in order to fill that out, I need to know the number of year 0 fish times the number of babies they have. And then I add that to the number of year 1 fish times the number of babies they have. And I add that to the number of year 2 fish times the number of babies they have, plus the number of year 3 fish times the number of babies they have, and so on and so on and so on. This does, I will make a side note, make the assumption that breeding occurs before mortality. But if I fill all that out, what I basically find is 14. This is exactly the same example we saw before where we had 7 year 1 fish. And so my total population size next year should be 14 fish that are year 0, plus about 5 fish that are year 2, or about 19 fish. So there's my population in the next year. And I want you to take a note. I want you to notice that 2 things have changed. First, the total size has changed. I've gone from 7 fish in year X or year 1 to about 19 fish in year X plus 1 or 2. But I've also changed my age structure. I had all year 1 fish in year X or year 1, and now I have absolutely no year 1 fish. I actually have 14 year 0 fish and about 5 year 2 fish. So both my population size and my population age structure have changed. So that was going from year X to year X plus 1. Maybe it's from year 1 to year 2. It could have been from year 2 to year 3. It could have been anything. It's going from one year to the next. How do I figure out what happens the year after that? Well, I just kind of rinse and repeat. So I move all of those X plus 1 years over, and I start from there. So I'm starting now from a population where I have 14 year 0 fish, no year 1 fish, about 5 year 2 fish, no year 3 fish, no year 4 fish, and I want to do the exact same thing. To calculate the number of year 1 fish I expect 1 year later, I take my year 0 fish times the probability they survive. To calculate the number of year 2 fish, I take my year 1 fish times the probability they survive. To calculate my expected number of year 3 fish, I take my year 2 fish times the probability they survive, and so on and so on. And I get numbers. And then, again, to calculate the number of newborns, I cannot figure that out from the age class beforehand. The only way I get newborn fish is by births, and so I use fecundity, and so I take the number of year 0 fish times the number of babies they have, plus the number of year 1 fish times the number of babies they have, number of year 2 fish times the number of babies they have, and so on and so on and so on. Add it all up. That gives me my total number of babies, which in this case is 4.69. So again, you'll notice that my population size has changed, and my population age structure has changed. And so we can go on and on and on like this, year after year, calculating the change in the population size, the change in the population age structure, over and over and over, basically until the end of time. So that's not super fun. But let's show it for a number of years. So here, I started with that same population where I had 7 year 1 fish. I calculated the number in each age class after 1 year, after 2 years, 3 years, 10 years, 20 years, and 30 years. And you'll notice something, especially if you look at the last 3 columns. You'll notice that something starts to happen with the age structure. And it actually starts to stabilize. So I end up with about 6 year 0 fish for every 3 year 1 fish, for every 1.6 year 2 fish, for every 0.6 year 3 fish, and so on. And so what eventually happens is that the ratios of the different ages begin to stabilize. So if I take my year 1 fish divided by my year 0 fish, or if I take my year 0 fish divided by my year 1 fish, doesn't matter, I should get the same ratio. I should get that same number year after year after year after year. And when that happens, we say that the population has reached a stable age distribution. In other words, we don't get these rapid swings in the number in each age from one year to the next. So if you look at the first couple columns, I go from having 7-year one fish to no year one fish to 8-year one fish to 2-year one fish. I got rapid swings. But after a while, I keep increasing, but the ratio between them doesn't change. All right. So again, you might wonder, did Dr. Bewick sit there and calculate sort of the next year population 30 times to get that previous table? Well, I didn't. So what I did is I used what we call a matrix. And I won't expect any of you to use a matrix, but for those of you who are comfortable with matrices, for those of you who maybe are engineers, who use matrices all the time, survivorship can actually be represented as a matrix. All those survival rates, survival rates can be represented as a matrix. And what you can then do is use that matrix and apply that matrix over and over and over to a vector of your different numbers in your different age classes. Well, that's great. That doesn't seem to help. That seems like it'd be just as much work because I got to keep multiplying that matrix by the vector, matrix by the vector, except that the nice thing about matrices is that you can actually raise them to powers and do the calculation much quicker. And so actually you can calculate the number 30 years later very, very quickly if you know how to manipulate matrices. Again, I would not make you do that, but it's something to know. All right, so the final thing we're going to do is we're going to work out one more example in class. If you did not go to class, I would suggest strongly that you try to work out this example so that you know how to manipulate these life tables. And if you can't, I would suggest that you look into that and get some help. Otherwise, that's the end of this lecture, and we will talk about population growth a little bit more in the next lecture. In the meantime, if you have any questions, I'd encourage you to email me at sbewick@clemson.edu.